Bismillahirrahmanirrahim. Today I'm going to explain a new topic, that is coordination compounds. What they are, what is the chemistry behind the formation, the preparation, synthesis of the coordination compounds, how they are prepared, and most importantly, what are their application, how they are important to us, especially in case of their biological applications, their medicinal applications, their catalytic application. They are a sort of a show a diverse range of catalytic activities. Similarly, they show a diverse range of medicinal applications. They are antifungal, antibacterial, anti-cancerous, anti-diabetic, and so many other applications they do show in area of the medicinal chemistry. So what the coordination compounds are, that's what my today's topic. I will try to introduce you how actually the coordination compounds are formed, what they actually are. For such compounds, actually, you need to have a sort of a metal atom, central metal atom, and this metal atom carries coordinate covalent bond, with certain other anions or neutral entities, like, and those are called ligands. I can represent it as L means ligands, they are called coordination compounds, where central metal atom has coordination bond, coordinate covalent bonds with certain other anions or neutral group of atoms, and they are called ligands. And this compound is supposed to be called as coordination compound. So coordination compound is supposed to be something like that, where a central atom is supposed to be a metal. Mostly they are the transition metals, D block metals, having variable valencies. They are supposed to be those metals, and these are the ligands, the ligands who provide lone pair of electrons for coordinate covalent bond formation, So it's a sort of a coordinate covalent bond formation. It's a sort of a coordinate covalent bond formation where this gentleman, the ligands, they provide lone pairs. As I've told you, those ligands which are surrounding the central metal atoms, those ligands could be anions, means they are supposed to be electron rich. Either they carry negative charges, they are in the form of anions, or at least they do carry lone pairs, which can be donated to the central metal atom. As a result, there will be a coordinate covalent bond formations, and the resulting whole compound will be called as a coordination compound, coordination complex, coordination compound. So this is what it could be. As I've told you, the ligands can be anions, or they could be neutral group of atoms. What does it mean? I want to just explain in next few minutes or so. You have an idea about this buddy? One could imagine the formation of this coordination compound, central iron atom, and then you can see the water molecules only, simply the water molecule. H2O has provided lone pair. We have an idea the oxygens do carry those lone pairs. Those lone pairs has been given to the central metal atom, and we can say that there are coordinate covalent bond between oxygen and the iron, So this is how these bodies are supposed to be called as the ligands. As you have an idea, this ligand is a group of atoms, H2O, group of atoms. It's a neutral, does not carry any negative charge. So it is acting as a ligand because it is donating lone pair for the formation of a coordinate covalent bond with the central metal atom. So this is one of the requirement for the preparation of coordination compounds, coordination complexes. We must have a central metal atom. We have an idea the metals are electron deficient. They need electrons, they can accept electrons. So there must be surrounding ligands around the central metal atoms. Those ligands, as I've just told you, could be group of neutral atoms, but they have lone pairs which could be donated to the central metal atom. So there will be a formation of covalent bonds with the central metal atom. The resulting compound will be called as the coordination compound. So this is one of the examples, I can give you a few more examples, simpler one at the moment, just to show what the coordination compounds are, what is meant by a ligand, what is the central atom in fact. This is what we need to look around. A few more examples with me. Yes, in another example, again Fe has been taken as a central atom. People have used ammonia. We have idea that nitrogens do carry lone pairs, So it carries two ammonia groups, as ligands. One can imagine the presence of cyano groups, CNs, C triple bond ends, So they are present around. They must be in the form of negative charges. We have an idea they are supposed to be HCN, something like that in the neutral form. So once they can be in this form, they can coordinate. Then it means what I'm trying to say, the ligands can be in the form of the negative charges carrying anions. They could also act as anions. Oh, sorry, they could also act as ligands. They can generate covalent bonds with the iron, So this is how the coordination complexes, coordination compounds are generated. uh, by the coordinate covalent bond between the central metal atom and the ligands. Ligands are those entities which can donate actually the lone pair of electrons to the central atom, central metal atom, so that there could be a covalent bond formation, coordinate covalent bond formation actually. So this is how they are supposed to be in uh, coordination compounds, coordination complexes. It's a mixed sort of entity. Over here you can see the buddies who have the lone pairs, neutral entities, whoever they could be from in the form of anions. All together they're acting as ligands in this coordination compound, This is the basics about the coordination compound, where central metal atom is connected with ligands who can donate electrons. Let's say this sort of organic compounds, we have an idea that these carries an amine groups having lone pair of electrons, at the both sides, at the both ends. So what could be done? These two buddies could act as lone pair donors, as we have ideas that they can donate their nitrogens. So if you have any metal atom over there in the center, so it can make a bond over here, it can make a bond over here. Okay? A single molecule, single ligand can have two coordinate covalent bond with the central metal atom. So same could also be done. Let's say we have another molecule of the same entity. So they can have something like that. Again, lone pair donors are around, So this is also a sort of a coordination compound, and organic based, the organic molecule can coordinate with the central metal atom through two donors of the lone pairs, two coordinate covalent bonds 2 and 2. This is how it could be. Mean same sort of, the ligands could be of the same sort, ligands could be of different sorts, they could be mixed one, as I've given you an example, that the last one where ammonia and cyano groups have been used as ligands. Over here the amino groups are being used as lone pair donors, so they could also act as ligands for the formation of the coordination compounds. So this is the basic about the coordination compounds actually. The coordination compounds are those compounds where we will have a central metal atom, M mean a metal atom, usually transition metals of D block, As we have ideas, metals are electron deficient, they need electrons. So we need to bring somebody around who has the capacity to donate electron, mean they are electron rich entities. So they can donate electrons in the form of lone pair. So somebody who donates lone pair means they generate coordinate covalent bonds So the coordinate covalent bonds are formed with central metal atoms, and the resulting compound is supposed to be a coordination compound. This is one of the examples, you know. Few more examples could be cited just to clarify the concept, you know. There are so many metals around which have been used for the preparation of different types of coordination compounds, like cobalt has been used as such, you know. Similarly, ammonia is very frequently used, you know. As I've told you, it has the capacity to donate electron lone pairs so easily, you know. Being basic in nature, the metals are electron deficient. This is also one of the example where central metal atom has got coordination bond with neutral ligands as well as anionic ligands. So this is how the coordination compounds could be prepared, could be synthesized using different sort of ligands, you know. The coordination compounds, why we are looking into the chemistry of the coordination compound. One very important aspect about the coordination compound is their uh, very important as far as nature is concerned. They are available in the nature. Let's say hemoglobin, heme molecules, they carry uh, coordination compounds. Similarly, we have an idea about the photosynthetic pigments, you know, those also do carry chlorophylls, they do carry coordinated compounds as well. So coordinated compounds are frequently available around us in nature. uh, Natural product chemistry, where organic ligands have complexes with central metal atoms. Organic complex, organic ligands, you know, that what I've discussed over just a simple, a brief one. However, in the nature, the coordination compounds have been developed using a bit complex organic ligands along with central metal atoms like iron in case of hemoglobin, and magnesium, I think, in case of chlorophylls. So this is how the coordination compounds are important as far as the nature is concerned. That's why I'm trying to give you a sort of an introduction about the coordination compounds, how they're prepared, how actually they're formed, what is the basic about it, and then I will go through about their applications, especially as far as their biological applications are concerned, you know. Now let me explain the chemistry, the structure of the hemoglobin, heme molecule, so you may get an idea about the ligands and the coordination between the ligands and the central metal atoms, just for your uh, concept building purposes, you know. This body is called pyrrole, you know, a five-membered ring containing nitrogen, where nitrogens are available in the ring with their right the way. This sort of the compounds, okay? They are available. We have CH3s around. You need to have CH methylene group groups between the carbons and the carbons. This is how they look like, you know. I'm trying to build a heme molecule for you guys, how it looks like. This is what I'm trying to convey to you guys. In the central there is going to be an iron Fe over there, you know. This is how it is going to be. The you need to install one methyl group over here. Yes, you can have methyls. Leave one again, you need to put in methyls here, you know, and then we can have methyls over here. Then we have CH2, and then we have hydroxyls OH. In this fashion, similarly we have CH2 OH. Similarly, we can have a vinyl group, that is CH, and then we have a CH2. Over here we have CH, and then we can have a CH2. This is how it is look like, the structure. The nitrogens, they do make two nitrogens actually made bonds through dotted lines. The other two nitrogens generate coordinate covalent bonds. This central atom is supposed to be actually in the form of +2 oxidation state. That's why two are the dotted line bonds and the other are two the coordinate covalent bonds produced there. So this is how it is supposed to be. So you can see it's a bit complex structure. This is a sort of a natural coordination compound, you know, present in nature. It's a hemoglobin. It's a heme molecule. Just I've given you, it's supposed to be sort of double, single, then it is something like that, you know. There's going to be sort of a double bonds between these and these ones as well present over there, just to complete their valencies. We need to generate the double bonds here as well. So this is how it looks like. One can have the pyrroles having methylenes, CH3s, methyl groups, you know, and then two of the rings do carry vinylic substituent CH2, and the two of the carbons really, they do carry, I think they're supposed to be, let me check once. Yes, they're supposed to be actually, they are the carboxylicases, COOH. Yes, they are supposed to be the carboxylicases, actually not the alcohols. Sometimes they do, sometimes they are in the form of dissociated form of either COO negative. In fact, they are supposed to be the acidic group. Okay, so this is how they are supposed to be. So it's very easy to draw. You may check from the online sources if there is any irregularity in this structure, please. I don't mind if you check it out, cross-check somewhere from the other sources. So this is what I'm trying to convey, that it's a central metal atom. Okay, as far as our requirement is concerned for the coordination compound formations. What is next? The next are the ones who could donate electrons. What those are? The nitrogens. The nitrogens do carry lone pairs. In this case, those nitrogens are not the simpler ones as usually we would have. We can bring in ammonias having lone pairs. So yes, they can generate, similarly they can generate coordination compounds. That's very much true. However, once you change the nature of the ligands, we have the nitrogen, but nitrogen is a part of a ring system. If it's a part of a ring system, then obviously its nature will be changed. The nature of the resulting molecule will be changed. Nature means its physiochemical properties will be changed. So every coordination compound, depending upon the nature of the ligands, will have a different physical as well as chemical properties. Physical properties means especially we have an idea the coordination complexes or coordination compounds, they do appear as colors. They produce some sort of colors, They are the colorants. So the pairs of the central metal atom as well as the ligands, they do determine the nature of the color, the appearance of the color, in fact, nature of the ligands, nature of these metal atom, coordination number, that determines its physiochemical properties, chemical properties, better, and the physical properties, yes, specifically the appearance of the colors, they do depend upon the nature of the ligands. So once we have used simpler ligands, definitely they will have their own properties. Once you change the ligands with certain complex systems where there is unsaturation is also involved, single, double, single bonds are involved. There are certain acidic entities are also available which can undergo dissociations, creating negative charges. At the same times, we have also nitrogens with their lone pairs. We have a vinylic parts as well, which can have a double, single, double, sort of a resonance structures formations. So all is going to put in their share in the cumulative physiochemical properties of that coordination compounds. That is why the coordination compounds are important, especially in medicinal chemistry. They have supposed to show a number of biological activities. They have also been known as an efficient catalyst in a number of organic synthesis. They're also involved as especially in electrical appliances, LEDs, OLEDs, they're frequently used because they can produce colors, as I've just explained to you. So this is all about the basics of the coordination compounds. What is basic? There should be a central metal atom, there should be a surrounding ligands. Those ligands could be neutral entities as ammonia, as water molecules, or any other organic molecules having neutral amines or any other donors, lone pair donors, or there could be anions like chlorides, cyanides, any others are also involved for the preparation of coordination compounds. So the ligands nature, whether they are complex ones or they are the simpler ones, whether they are the neutral ones, whether they are the anionic ones, they all do put in their share and influence actually the cumulative effect in the form of unique physiochemical properties of that coordination complex. So in the next lecture, inshallah, I will do explain a few more example of the coordination compounds, and I will explain their applications in the field of medicinal chemistry and their use as catalysts as well, inshallah. So you will understand a bit more about the coordination compounds, coordination complexes. I'm just trying to give you a brief overview about these compounds and their important application. The rest you will offer a separate course on coordination chemistry, uh, coordination complexes, um, complexes of heavy metals, something like that. So this is going to be in your next semester, inshallah. So at the moment, as a part of my course, I'm to give you just a brief overview. So that's what I'm trying to give you. Okay, thank you very much. Hope you got the idea about today's topic. If you have any question, do ask me. Just put in your comments, your question in comment area, or you may approach through WhatsApp. I will be available, inshallah, for your convenience. Thank you. Assalamu alaikum.